I'm using scikit-learn's sparse function. I'm giving it my data, a dictionary, and setting the L1 regularization strength, ALPHA, to 1.0. I also want at most 5 non-zero coefficients per data point, NNONZEROCOEFS. This function will find a sparse representation of my data using the dictionary. The output of sparse will be a matrix with 1000 rows, one for each data point, and 50 columns. Each row represents the sparse coefficients needed to reconstruct the corresponding data point using my dictionary. Pretty cool, huh? This is my dictionary matrix. It has 100 features described in a 50-dimensional space. Each column is a feature, or atom, used to reconstruct my data points. This is my data. I have 1000 data points, each described by 100 features. It's this data that I'm trying to represent sparsely using my dictionary. I'm using scikit-learn's sparse function, a powerful tool for finding a concise, sparse representation of data. It's like summarizing a long story with just the key points. This represents my data. I have 1000 data points, each described by 100 features. Imagine 1000 pictures, each with 100 pixel values representing its properties. This is my dictionary, a set of 50 basic building blocks, features, each described using 100 values. Think of 50 unique Lego bricks that I can combine to build things. Here, I'm applying the sparse function. I feed my data and dictionary to create the sparse representation, setting ALPHA to 1.0, which controls sparsity and limiting each data point to at most 5 non-zero coefficients using NNONZEROCOEFS. This is the result, a 1000 by 50 matrix, where each row tells me how to combine my 50 Lego bricks, dictionary entries, to best represent each of my 1000 data points. The sparsity means most entries in each row will be 0. This parameter controls how sparse the representation needs to be. A higher ALPHA means I favor a solution with only a few non-zero coefficients. It's like preferring a simple Lego model over a complex one. This sets a limit on the number of non-zero entries in each row of my resulting sparse code matrix. It's similar to limiting the number of Lego bricks that can be used in a single model. I'm using scikit-learn's sparse function, a powerful tool for finding efficient, compact representations of data. It's like summarizing a long story using only the most important keywords. I have 1000 data points, each described by 100 different characteristics or features. Think of it like 1000 people, each with 100 different attributes such as height, weight, age, etc. I have a dictionary, a matrix, that helps me represent those 100 features in a smaller, 50-dimensional space. It's like having a codebook to translate the 100 features into a more concise, 50-feature representation. These are the settings I use to fine-tune the sparse function. This alpha parameter controls how much I want to encourage sparsity. A higher alpha means a stronger preference for sparse solutions, more zero coefficients in the result. It's like saying, only use the most important keywords, get rid of the rest. This tells the function that each data point should have at most 5 non-zero values in the final representation. Use at most 5 keywords to summarize each story. This is the function that does the magic. It takes the input data and dictionary, and using the parameters, generates a compact representation. The result is a sparse code matrix that represents each of the original 1000 data points using only 50 components. This is the compact, simplified version. It keeps only the essential information from the original 100 features. I'm using scikit-learn's sparse function, a powerful tool for finding a compact, sparse representation of data. It's like summarizing a long story using only the most important keywords. This is my data. It's a table with 1000 rows. Each row is a different data point, and 100 columns. Each column represents a feature or characteristic of the data. Imagine it like a spreadsheet with 1000 data entries, each having 100 pieces of information. Think of this as a codebook. It's a matrix with 100 rows, matching the number of features in my data, and 50 columns. Each column represents a basic building block or atom that I use to reconstruct the original data in a much smaller, more efficient way. It's like having 50 basic words to represent any concept. Here, I'm applying the sparse encode function. I'm giving it my data and the dictionary. The alpha parameter, set to 1.0, controls how sparse I want the result to be. A larger value encourages more sparsity. The nonzerocofs parameter, set to 5, limits the number of non-zero values in each row of the output to at most 5. This forces it to use only a few of the dictionary atoms when reconstructing each data point. This is the result. It's another table, this time with 1,000 rows, one for each data point, and only 50 columns. Each row contains the coefficients, the weights of each atom, from the dictionary, that combine to reconstruct the corresponding original data point. It is much smaller than the original data, which is the beauty of sparse encoding. This is correct. I have 1,000 data points, and my sparse representation uses 50 atoms from the dictionary. This is incorrect. While I'm aiming for at most 5, it might not always be exactly 5. Absolutely correct. The alpha parameter tunes the strength of L1 regularization, directly influencing how many near-zero values I get in my sparse code. Higher alpha means more sparsity. This is also correct. Increasing nonzerocofs lets me use more dictionary atoms for each reconstruction. This could reduce the reconstruction error, but it makes the representation less sparse. I'm using scikit-learn's sparse encode function to find a sparse representation of my data. It's like finding the most important ingredients in a recipe. Instead of using all of them, I select only the key ones to capture the essence of the dish. I have 1,000 different data points, and each one is described by 100 different features. Think of it like having 1,000 people, each with 100 different characteristics like height, weight, age, etc. I want to represent these characteristics using less information. This is a special matrix, dictionary, that helps to compress data. It has 100 rows, matching the 100 features of my data points, and 50 columns, meaning it represents data in a 50-dimensional space. It acts as a codebook, using 50 atoms to represent 100 original features. Here, I'm applying the sparse encode function. I'm feeding it my data and the dictionary. Alpha equals 1.0 is a parameter that controls how sparse my final code will be. Higher values mean more sparsity, and n underscore non-zero underscore cofs equals 5 means I want at most 5 non-zero values per resulting data point. This is the result from applying the function. It's a new matrix with 1,000 rows, one for each data point, and 50 columns, representing the reduced dimensionality. Each row shows how to reconstruct the original data point using a combination of only a few atoms from the dictionary. This parameter, alpha, adds a penalty to my solution based on the sum of the absolute values of the coefficients. A higher alpha forces more coefficients to be 0, resulting in a sparser representation. It's like adding a tax on using too many ingredients in the recipe. This parameter, n underscore non-zero underscore cofs directly limits the number of non-zero elements in each row of the final sparse matrix. It's like saying I want to use at most 5 ingredients in each recipe, even if more would make it better. We have 1,000 data points, each described by 100 features. I think of this as a big spreadsheet with 1,000 rows and 100 columns. This is a matrix with 100 rows and 50 columns. It represents a set of 50 features that we can use to represent the original 100 features in a more concise way. Each column is a new building block or atom. I'm super excited to tell you about this. These are settings for the sparse underscore encode function. Alpha controls how much I want to prioritize a really sparse solution. A larger alpha makes the solution more sparse. Backquote n underscore non-zero underscore cofs backquote means that in the compressed representation, I will have no more than 5 non-zero values for each data point. This is the amazing result. After crunching the numbers, I get a new matrix with 1000 rows, one for each data point, and 50 columns, one for each of the new atoms from the dictionary. This represents the original data in a more compact form. This is the original data. It's a large matrix that we are going to try to make more compact. This is the function from scikit-learn that I use to do the magic of converting from the original data to the compressed representation.